So we're continuing on with geometric series. Just a reminder, once we talk about series, we're now doing the summation. Some math people will call it summation notation, but it is the sigma symbol. So just as a reminder, geometric series now has a common ratio, which means we're multiplying over and over again. So what this notation is we're plugging 1 in for I, so we're doing a sub 1 plus a sub 2 plus a sub 3, and we continue on until we get to this top number, a subscript 5. Now they tell us what the first number is in this pattern, it's 3, but then the next number is defined recursively as double 3. So our common ratio in this problem is 2, which is why the second number is 6. And then the next number is double the 6, the previous term, 12. The next number is double. So I hope you realize where the doubling is coming from. It's from the common ratio, where the summation, the adding, comes from the sigma notation. Or if you want to call it summation notation, that's fine if you like to rhyme. But this isn't as nice as the arithmetic. You can't just do the rainbow addition because it just doesn't work that way. Probably the best option for you, and you're allowed to use a calculator, is just to add. But if you notice, we do 3 plus 6 is 9, plus 12 is 21, where we have 45 with that, and then plus 48 should give me 93. I'm just double checking because I always second guess myself. Yeah, it came out to be 93. So before just telling you what the formula is, which I guess I could do, it's already on the next page, I think you guys are smart enough to realize and to really understand this formula. So what they do is they first come up with a new term, and they call it capital S, S subscript n, to stand for the summation of all of these terms. And the way they came up with this formula is kind of ingenious. But what they did is they first started by taking this term and multiplying both sides by r. Well, think about it. If you multiply both sides by r, what you're really doing is I'm going to distribute an r into all of those terms. So r times a1 plus r times well, how about this? A1 times r squared. Let me move this r on this side. And I hope you realize what I'm doing is I'm multiplying each one of these terms by r. So the next one would be a1 times r cubed, so on and so forth. And then this one is a1 times r to the n minus 2 plus 1, so it becomes n minus 1, and then plus a1 r to the n minus 1 plus 1, so it's to the nth power. Because notice that each one of these exponents is adding 1 to that term. So then here's sort of the ingenious part to it, is that they rewrote that as s of n minus r times s of n. So s of n is considered the a1 plus a1 times r plus a1 r squared, so on and so forth. a1 r to the n minus 2. I didn't give myself enough room. But I think what you'll notice is I'm going to subtract off the r times s of n. So I'm subtracting off this piece, a1r. I'm subtracting off this piece, a1r squared. And you can see that all of these pieces will cancel all the way until the very end. The only thing that doesn't cancel is this piece right here, the a1r to the n power. And maybe I could have wrote that a1r to the n minus 1. I hope this is making sense. If it's not, don't worry. We will get to the final answer here shortly. So what I'm saying is s of n minus r times s of n is equal to everything canceled except for the a1 and the last term, a1 r to the nth power. So let me put a little box around that, because now we're going to do a quick trick. Is what they do is they factor both sides of this equation. So this is a true statement, believe it or not, and you can factor out s of n. Whoops. Okay, I need to stop making mistakes. And I'm left with 1 minus r. So look at the left side. Is if I distribute s of n in there, will I get the same thing? And yes, I will. And on the right side, I could also factor out an a sub 1. I'm left with 1 plus... Oh, whoops. This should have been a minus. Stop making mistakes. Sorry if you're writing all this down. I should just redo this, because I've made so many mistakes at this point. But this should have been a minus, because remember, we were subtracting every one of these terms. And I forgot to write subtraction there. Now I'm almost done, because I want a formula for s subscript n. Well, if I want to solve for s subscript n, the quick answer would be to say, well, it's a multiplication problem, so just divide that piece over. And this is the exact formula. And if you got stumped along this explanation, don't stress about it. You can use this formula, and the formula is right here as well. That's why I knew I made a mistake when I didn't have that minus in there. I knew what the formula was. I have it memorized. You don't have to memorize it, because I'll either provide this, or you can use your notes while you're doing this problem. But this is exercise 2 explains where the formula comes from, and as long as you don't make a silly mistake like I did, you can understand how to get this formula. So let me just go back and redo exercise 1, because all we needed to know what the first number was. That's a sub 1 in our formula. We need to know the ratio, which they told us in the problem was 2, and we needed to know how many terms there are. Well, in exercise 1 there were 5 terms. So let me just rewrite the formula. A sub 1, 1 minus r to the nth power over 1 minus r. So if you use that formula, knowing that the first term is 3, 1 minus the ratio is 2 to the 5th power, all over 1 minus 2. And I'm just going to use a calculator. I'm not trying to get fancy on this problem. Just 3, 1 minus 2 to the 5th power, just close the parentheses, over 1 minus 2, and you get the right answer. And that's what we're going to investigate on some of these. So what's the sum of this geometric series? So they have to tell you that's geometric. We now know that n is 8. There's 8 terms. The first term, so a sub 1 is 3, and the common ratio is 4. So we have the formula, and we can go straight into it. So it's 3, 1 minus, the ratio is 4 to the 8th power, all over 1 minus 4. And that's what I like about your graphing calculators, is you can easily just go in there and just change a few things around, and you get the right answer. Now, just so you're aware, you could have figured this out on your own, because you could have done 3 plus, the second term would have been 3 times 4, which is 12, plus the next term would have been 12 times 4, 48. And you could have done this over and over again until you get to the right answer, but I certainly like having a formula, and I hope you do as well. So, option 4. So I'm not trying to rush through these notes, but I think I can do at least exercise 4, and then I'll save the rest of this for the video. So again, second video, you might want to star this formula, put a box around it, write it down, and go from there. Just make sure you understand that a sub 1 is the first term. The common ratio you might need to find, like in this one, you need to figure out the common ratio in the problem is 2. and then the number of terms. Well, if you look at exercise 4, they don't tell you how many terms there are, which is where the other formula that we learned previously is going to come into play. R to the n minus 1 power. And I'll leave that ratio in there. So this is the formula for a geometric sequence. Notice I'm using the word sequence there because I'm not adding these together. And we can use this to figure out what the nth term would be. So that would be 768. It's the last term. We know the first term is 6. What we don't know is what that ratio is. Oh yeah, we do know what the ratio is. It's 2. 6 times 2. So times 2 to the n minus 1 power. So I'm just going to do, you could actually use logs to figure this out. We've already learned about logs. The fast way, though, would just be, okay, 768 divided by 6, the first term. So we're looking at 128 is equal to 2 to the n minus 1 power. So this should be a fairly nice number. I guess I could refresh how to do logs real quick, but what you could do is change it into log base 2 of 128 to figure out that that's equal to 7. Remember that this is an exponential form. Log base 2 of 128 is equal to n minus 1, which is why we typically teach sequences and series after learning about logs. But you could have also figured out that 2 to the 7th power equals 128. Let's just refresh that we did that at some point as well. So that means that n minus 1 needs to equal 128. I said that wrong. N minus 1 needs to equal 7. I'm trying to squeeze it right here. So that means the number of terms in this problem is 8. Now I'm just underlining it because it's not my final answer. We know our first term is 6, our ratio is 2, and the number of terms is 8. Now, I've had students in the past that are not very good at solving this, and they'll just guess and check. What do I mean by that? Is they start with, okay, the first term is 6 times 2, 12. So that's your second term. Third term. Fourth term. Fifth term. Sixth term. Seventh term. Eighth term. And they just use their calculator and they figure out that the 8th term by continuing on. And these numbers are usually pretty nice. Okay. So as I'm doing, let's see, we're finding the series. So that's the sum. So the sum of these first 8 terms is equal to the first term, 1 minus the ratio to the 8th power, all over 1 minus your ratio. And again, just type it in the way it looks and you'll be fine. 6, 1 minus 2 to the 8th over 1 minus 2. And the sum is 1530. I also realize that some students will literally go through their calculator and they'll add together, 6 plus 12 plus 24 plus 48 plus 96 plus 192 plus 384 plus 768. Assuming all my numbers are correct, but I'm just showing you that that answer was correct with a formula. So hopefully I didn't make too many mistakes and you're okay with my explanation, and I'll see you in a second video to explain exercise 5 and 6 to get you ready for the homework. And again, this is your formula that you're using for a geometric series.